Hello everyone. Today I will be discussing energy decomposition schemes and wave function analysis within ORCA. So I will highlight some updates in ORCA 6.0 and also some real-life applications, particularly involving the local energy decomposition scheme at the DLP Capo cluster level. And I will also use this chance to give you a sneak peek into some features coming in future releases that we are very excited about. Now that the foundational work is complete. So first, a bit about myself. So after several very rewarding years as a research group leader in Frank Nice's department, I finally moved to the University of Perugia, where the main focus of my research group that you see here is on catalysis and quantum mechanical methods for catalysis. But we are also interested in non-covalent interactions and biosystems. And we are especially interested in solving challenging chemical problems that cannot be easily addressed with standard computational methodologies. So if you're curious about our work, you can find the link to our social media here. Now, before diving into the details, I want to acknowledge the team behind this work. So what you will see today is the result of a true collaborative effort. And I'm very grateful for the contributions of everyone here, particularly Christoph Ripplinger for sharing some of his slides with me. Now, the presentation is divided into three parts. First, I will discuss some enhancements in the DLP Capo cluster methodology that have improved the accuracy of electronic energy calculations involving transition metals in ORCA 6.0. Next, I will explore advances in the local energy decomposition scheme, which, as you know, has found many applications in the study of non-covalent interactions. And finally, I will share with you some personal perspective on future developments in this area of chemical research. So, what's new with DLP Capo cluster? First of all, I believe everyone here is familiar with the methodology, so I won't discuss any detail, but I just like to recap briefly that this is a local correlation variant of CCSD parentheses T, which enables the calculation of Capo cluster energies and properties for systems with hundreds of atoms, because it is linear scaling or near linear scaling depending on the system. Now, this approach has found widespread applications across many fields of chemical research, and we frequently use it in our own research, especially when dealing with systems where it's unclear which exchange correlation function may be best suited for a given application. Now, in terms of accuracy for systems involving main group elements, DLP Capo cluster method achieves sub-kilojoule per mole precision when compared to Capo cluster results, canonical Capo cluster results, for relative energy calculations, such as reaction energies, barriers, and ionization energies. And this is especially true when used in conjunction with the P&O extrapolation scheme, which is discussed in this reference here. So if you don't know what I'm talking about, suggest you have a look, especially if you're interested in computing reaction energies or relative electronic energies with high accuracy. Now, for systems containing transition metals, DLP Capo cluster also performs with similar accuracy within the range of applicability of canonical Capo cluster. However, we did find a few pathological examples involving first-order transition metals. In particular, for complexes involving these metals, so first-order transition metals, it turns out that the correlation energy from electron pairs containing the semi-core 3s 3p orbitals is critical and requires special care. So to address this, we now localize separately these orbitals, and for them we use more conservative P&O thresholds by default in the correlation treatment. The details are described in the paper reported here, and I want to mention that this is now the default behavior in ORCA 6.0. Now, as an example, consider the zinc atom. Now, this figure on the left shows the percentage of correlation energy recovered by the DLPNO approximation for valence-valence, semicore-semicore, and semicore valence correlation with respect to canonical couple cluster as a function of the thicket PNO threshold, which is the threshold controlling the size of the virtual space in DLPNO couple cluster calculation. Now, you can see that recovering semicore correlation is very challenging, especially with large thicket PNO thresholds. Now, this led, in some critical cases, to significant deviations between canonical and DLPNO couple cluster for systems containing first-row transition metals. And so we have addressed this aspect in ORCA 6.0. Now, with the new ORCA 6.0 defaults, as you can see, the accuracy of the DLPNO calculations for systems containing first-row transition metals is significantly increased. In addition, in many cases, it turns out that calculations are actually faster with these settings than with the previous ORCA 5.0 defaults. The reason is that more conservative PNO thresholds for these orbitals typically lead to fewer couple cluster iterations to achieve convergence, which result often in significant savings in computational time. So to summarize, the new default for the DLPNO settings in ORCA 6.0 are more reliable for studying systems containing first-row transition metals, and also provide calculations that are typically more accurate and efficient compared to ORCA 5.0. This concludes the first part of my talk, and in the second part of this presentation, I will now discuss the current status of the LED scheme in ORCA 6.0 and future aspects of our research in this field. The local energy decomposition allows us to break down the electronic energy computed with local approaches into intrafragment and interfragment contributions. And this scheme has found widespread applications in the study of non-covalent interactions, some of which have been discussed and examined in this recent review article. Now, before diving into the new aspects of this feature, I will briefly recap the main idea of the approach with one example. Now, a common application area of the LED scheme is decomposing binding energies between subsystems into contributions from individual fragments and fragment pairs. For example, consider the interaction of a protein with a ligand. And with LED, the first thing we have to do is to divide the system into fragments, such as the ligand and the key residues in the active site. And then we can compute the binding energy between the ligand and the protein at the DLPNO couple cluster level and use LED to decompose this binding energy into contributions from individual fragments and fragment pairs. Now, in the decomposition, you will see one repulsive contribution per fragment, representing the electronic preparation. Now, the electronic preparation is the change in the electronic energy of the fragment ongoing from its ground state to the perturbed state it has in the protein-ligand complex. And additionally, we also have in the decomposition the interfragment contributions here, that represent genuine pairwise interactions, such as electrostatics, exchange, and dispersion. So for systems with many fragments, the results from the LED analysis can be represented graphically by means of the LED interaction maps. Now here is an example of these maps for the decomposition of the binding energy of the water hexamer. In this matrix, the diagonal terms represent the electronic preparation, so associated again with the change in the electronic structure, in this case of the water molecules upon formation of the cluster. And for example, the electronic preparation of water 2 for this example amounts to 41.1 kilocup mole. The off-diagonal terms instead represent genuine fragment pairwise interactions. For example, the strongest fragment pairwise interaction in this complex occurs between water 5 and water 6 and amounts to 72.6 kilocal per mole. This is a significant negative, so attractive, contribution to the binding energy, and represents all electrostatics, exchange, and dispersion interactions between the two water molecules. Now, using LED, these interactions, so electrostatics, exchange, and dispersion, can also be quantified individually to obtain additional physical insights. Now, this approach is extremely powerful, as demonstrated by the many applications that have been published over the years, but has some limitations that we have been trying very hard to address over the last few years. Now, one limitation is that we obtain the repulsive and attractive contributions as separate terms, leading to relatively large interaction values. So ideally, we would like to have the possibility to distribute the electronic preparation terms into the other fragment pairwise contributions in order to be able to estimate the net effect of an interaction between two fragments on the binding energy. So the approach that makes this possible is called fragment pairwise local energy decomposition scheme, and it is described in the paper reported here, which is currently still under review, but you can already access the paper on ChemArchive. Now, with this approach, we no longer have the diagonal terms because they have been distributed among all fragment pairwise interactions, but we have instead an exact pairwise decomposition of the association energy of the water cluster. For example, the strongest interaction in this system is between water 5 and water 6, and it amounts, if you account together for all attractive and repulsive terms, to minus 9.6 kilocal per mole. This is roughly twice the interaction for the isolated water dimer, and this difference originates from cooperativity of different non-covalent interactions within the water cluster that we can really quantify here for the first time. In contrast, if you look at the interaction between water 6 and water 2, you see that this is just 3.3 kilocal per mole, meaning that in this case the interaction is weaker than in the isolated water dimer, and this effect originates from geometric perturbation effects. So overall, this approach provides results that can be directly compared with experimental data and offers quantitative insights into the relative strengths of individual interactions and of cooperativity effects. So if you're interested in learning more about how to perform this kind of analysis, have a look at this ChemArchive paper here. Now, I would like to mention that being embedded within ORCA, clearly the DLP-NO cluster LED scheme benefits from any efficiency and accuracy improvements in ORCA 6.0 compared to ORCA 5.0, which you might find in the SCF, DLP-NO, and all related methodologies. So to give you an idea of what we can achieve now in a real-life application study, I'm about to discuss an example taken from a recent collaboration with our colleagues at the MIT. So in this work, we used LED to study the interaction between ribonuclease A and uridine oligophosphate inhibitors. So in this work, one of our goals was to decipher the influence of the oligophosphate chain length, so the number of phosphates, and of the individual polypeptides and nucleosides on ligand binding. So to this aim, our experimental collaborators synthesized a series of uridine oligophosphates with increasing chain length that you can see here, and provided us with very accurate structures for the protein ligand adducts. We then used the LED methodology to unravel individual interaction contributions to the protein ligand binding. Now, this system here is very challenging. It contains about 2000 atoms and it contains a negatively charged inhibitors. So it's a very complex case study. And in this work, we really wanted to describe everything using an electronic structure method rather than relying on empirically parameterized force fields. So we use essentially an anonymous approach. You can find the detail in the paper, where the ligand and the key residues in the active site are treated at the DLP-couple cluster level, while everything else is accounted for at the HF3C level. And in this work, we accounted for the implicit solvent using CPCM. Now, if we look at the trend of inhibition constants for the oligophosphates with increasing phosphate chain length, so from top to bottom in this table, what we see is a law of diminishing returns, where the uridine pentaphosphate, P5U, is experimentally the strongest inhibitor. Now, quite surprisingly, these inhibition constants correlate very well with our couple cluster protein ligand binding energy calculations. Now, this may seem surprising. Why? Because we have to consider, of course, the potential role of dynamic and entropic effects in this system. However, the fact that this correlation exists suggests that the non-covalent interactions that can be found in the crystal structure probably play a fundamental role in determining these inhibition constants. Now, the question is, what is the binding mechanism? So what are the individual interactions that contribute and determine the protein ligand binding energy? The power of LED is precisely that it allows us to disentangle these individual contributions from the residue in the proteins. So we analyze these interactions between the inhibitor and the residues for different inhibitors with different phosphate chain length, and we indeed found that some interactions are especially important for rationalizing the binding energy trend with the phosphane chain length. So as an example, a very important interaction is that of the oligophosphates with lysine, which in the case of P5U is the strongest interaction between the inhibitor and a residue in the active site. So if we look at the trend of this interaction for different oligophosphates, we see that the trend is analogous to that found for the binding energy, with a minimum located exactly again for Pi5U. So clearly the situation is a bit more complex than that, and we cannot explain the trend of binding energy simply using a single interaction site, okay? Because of course we have other protein-ligand interactions, and also the effect of ligand conformation must be accounted for, and there are other dynamic factors that are of importance here. However, this example demonstrates, I believe, clearly the usefulness of LED scheme for this kind of study, and it is especially important that now it can be used for a system of this kind of complexity. Now I would like to conclude this talk with some perspectives on future developments. So unfortunately, not everything we have been working on has made it to ORCA 6.0. But the foundational work is in place, and many new features will be released with ORCA 6.1 and future versions. So I would like to mention now a couple of these upcoming features, but I will leave out a few very important surprises concerning the LED scheme for which you will really have to wait for ORCA 6.1. The first new feature that I would like to mention is a tool for the atomic decomposition of the London dispersion energy. So at the DFT level, the analysis is already available through Python scripts that you can access via the GitHub link provided in the original publication. However, we will soon also release this feature within ORCA. In particular, in ORCA and only in ORCA, it will be possible to perform the atomic decomposition of the London dispersion energy extracted from the LED scheme. And this, I believe, opens up unprecedented opportunities for the detailed analysis of London dispersion effects in molecular chemistry. So in general, this approach allows us to quantify not only the contribution of dispersion from individual fragment pairs, as it is currently done in the LED scheme, but with this atomic decomposition, we can quantify for the first time the contribution from individual atoms within the fragment. So in this example here, we have analyzed the contribution of each atom in the imidacloprid ligand to the binding energy with a protein receptor. The analysis shows that the chlorine atom alone contributes with more than 10% to the overall dispersion contribution to the protein ligand binding energy. So I believe that this kind of insights could be very useful for the development of novel pharmaceuticals, but also in other fields like catalysis and material science. And so a final point that I want to make concerned the implementation of the natural orbital for chemical valence scheme in conjunction with the energy decomposition analysis in ORCA. Now, thanks to the major rewriting of the SCF code in ORCA 6.0, it was possible for us to rewrite from scratch the scheme in a way that is now more efficient and user-friendly, and also including a number of entirely new features that we are currently documenting in a manuscript, which I hope we should be able to submit soon. Now, unfortunately, we are still finalizing the last few touches with the idea of releasing a complete and black box methodology in the coming 6.1 release. So for the time being, this scheme is disabled in ORCA 6.0, but it will be back soon with many additional features and capabilities, so stay tuned. Now with that, I would like to thank you very much for your kind attention.